Hi guys, thanks for joining. So I would like to start this presentation with a quick introduction to the quantum boosting for classification, and then I would like to go a bit deeper into the cost function of the algorithm, and finally I would like to talk about a very simple possible implementation of this. So I will walk you through the relevant code and show how such kind of implementation can be used to solve both synthetic and real world problems with quite decent and comparable results. By comparable, I mean comparable with the classical results. And then I would like to open the floor for questions and discussions. So the quantum boosting classifier that I'm going to present is based on Nevin's paper from 2008. Ever since that, he has suggested many different improvements to the algorithm. But since I just want to show a very basic idea behind it and the very basic implementation of the algorithm, I would follow that first implementation. It would also make it easier for anyone if it's interested to understand how to build on that basic version and improve it further. And just like AdaBoost and XGBoost, the basic idea behind quantum boosting is once again to combine a bunch of weak learners and weak learners into a strong classifier. And the role that quantum or quantum inspired optimization plays in here is that these capabilities are used to find an optimal set of binary weights. So by binary weights, of course, that these are ones and zeros. So once the optimization ends, you know which classifiers are the ones whose decision will be considered and which ones are the ones that will be turned off. And these weights are basically found through minimization of this cost function that is shown here. The cost function itself, you can see, comprises of a quadratic term and a linear term. Now, I would like to describe a bit the terms here. The hi of x is an array of the size of the data set. So if the data set contains 1,000 examples, hi would have a size of 1,000, and each value is either 1 or -1, which corresponds to the binary classes. So hi of x is basically the predictions that specific learner gives to each of the data points in the training set. And xs is basically xs is one data point, and similarly ys is the corresponding prediction. So then there's a regularization term which is based on lambda. The goal of this term is to basically penalize complex models. By complex models, we mean the models that are overfitting to the training set. So by increasing the regularization term, you ensure that such models are penalized. There's an expansion of this equation, this cost function, that makes it even easier to understand, and that where is the quadratic term and what it represents, and where is the linear term and what it represents. And this is what I show here basically. So just with a couple of lines of algebra, the same cost function can be reformulated as this one shown here. You can see that with this representation, it's easy to see that there's a one correlation term for correlation between the learners, hi and hj. What we have got is, let's say we have got an ensemble of 10 learners. hi here represents, for example, the first learner, and hj the second learner. But in total, basically this creates a matrix of pairwise correlation between the learners. If we have got 10 learners, we would have a correlation matrix of 10 by 10. So what this term represents is basically um, the classifiers, the learners that are correlated, that are strongly correlated with each other, cause the energy to go up, and basically increases the probability for one of them to be assigned a binary weight of 0, for one of them to be switched off. Similarly, there's a linear term, and that is basically showing the correlation between the classifier's predictions and the ground truth. Ground truth here is represented by Y. So the greater is this correlation, the greater is the chance that that learner will also be assigned the weight of 0 and basically switched off. And this finally agrees with the general paradigm of ensemble methods, um, which promote diversification of the learners in the ensemble for an improved generalization. Is it clear? So there are two terms. There is quadratic term, which penalizes the learners that are correlated with other learners. And there's a linear term that penalizes the learners that are overfitting to the training set. That's what is in short. So if there are no questions, I would like to move on to the implementation. Okay, so I would like to show the implementation basically in the in a notebook that I have prepared. I'll just switch my screen to that. Okay, can you guys see the browser window?
Yes.
Okay, great. So first of all, I will start with creating an ensemble. An ensemble that can be trained using boosting and that can be used to do the prediction on the data set, a previously unseen data set. So I have this very simple class here that gets a number of learners I would like to have in the ensemble and the depth of the trees. So during the whole demo, I will be talking about ensemble of trees, which is why one of the parameters here is the depth. You could also have ensembles of KNNs, ensembles of SVMs as you like. But since we are talking about weak learners and boosting over an ensemble of those learners, the most relevant weak learner here is the decision tree. So basically, when I initialize this ensemble, I create an ensemble comprising number of learners decision trees. And then there's a fit procedure in the same class that trains them based on boosting, adaptive boosting. So what it is doing is that it trains the first learner, and this learner is then used to make prediction over the training set. And the second learner basically learns um, on the errors or misclassifications of this first learner. Similarly, the third learner learns on the misclassifications of the second learner, and in the same way, and the learning is done. Specifically, what happens is that once you have trained the first learner, let's say on 10 different examples, and it makes an error on 2 of them. So while training the second learner, what we do is that we increase the weight of those misclassified samples. and so that the second learner gets a data set with emphasis on those specific points. But in the same way, all of the learners are trained. This is classical boosting method. And in the predict method, basically, what is done is that all of these learners are used to make a prediction on a specific data point, and finally, a majority vote is done on their decisions. So let's say you have got 10 learners, and all of them say that this specific data point belongs to class A, except for two or three of them that they say that it belongs to class B. But since the majority says it belongs to class A, the decision is made in the favor of the majority. But this is, until here, it's totally classical, what we would get if we use scikit-learn's AdaBoost classifier. This is where it becomes different. If we see the quantum or quantum-inspired implementation, that now we work on that. Now we create the cost function that has got a quadratic term. You can see Hij here. And then there's a linear term, which has the regularization parameter. So quadratic term, what it is doing is that it's basically doing the first, it gets the prediction over the training set from each of the learners, and then it does a dot product between them. So this is a pairwise correlation between each of the learners' predictions. And then there is a linear term, just as I showed in the slides. So now what happens is that once we have trained the ensemble using classical method, and the next step is to basically calculate this cost function. So this cost function will be calculated, and finally we would have a matrix for the quadratic term and a vector corresponding to the linear term. And then that will basically be used to calculate the cost. So here we could use a quantum optimizer like D-Waves optimizer, D-Waves hybrid solver, or we could use, let's say, an optimizer from Pascal or IBM. Any quantum or quantum-inspired optimizer can be used basically. But just to keep this demo really simple, what I have done is that I have here written an exhaustive optimizer, and that goes over all of the possible combinations and calculates the cost for each of them. And basically the minimal cost, let's say, is found to the corresponding to a state where first 7 learners are switched on, and others are assigned a weight of 0 and thus are switched off. So that state will be returned from this optimizer. It will iterate over all the possible states. And since it will iterate over all the possible states, it's called exhaustive, and we don't have the luxury to have a really big ensemble. So the ensemble size will be limited by, and this will always be the case, that the ensemble size will be limited by the capabilities of the optimizer, which means if you are optimizing it or using D-Waves hybrid solver, you can go till, let's say, 1000, the size of 1000. But once again, the calculation would start to become slower and slower and slower. So there's a function that does the cost calculation, and there's an optimizer that gets the minimum state, that gets the state corresponding to the minimum cost. These are basically the tools that we need to now write the QBoost class. And so quantum boosting classifier, as you can point out at this point, is that it's basically a hybrid algorithm. There's a part of it that's classical that we went through here, and there's a part of it that could be quantum, but for the sake of this demo, I had just the exhaustive optimizer. So inside the quantum boosting algorithm, what we are doing is that we are just basically um, we first train the classical ensemble, and then inside the fit method of the quantum boosting classifier, we basically run the optimization process to get a list of ones and zeros that dictate which learners will be switched off and which will be kept on. And finally, we have got a prediction function, which is doing the same thing as the classical ensemble class here, doing the majority voting. Okay, so this is just a very simple implementation, and now I'll show you how we can use it to solve a synthetic problem and then a real world problem. Is there any question until now? Okay, so for a synthetic problem, I have chosen um, a very well-known problem of classification of moons. This is a synthetic data set that scikit-learn provides. What it does is that it makes two interleaving half circles and creates um, a situation where you have to use your classifier to find a non-linear decision boundary. So the decision boundary is a bit is not like friendly linear decision boundary. And the good thing is that these tools also provide you the possibility to include noise if you want, and you can shuffle the data set as you like. So I just generate that data set. That's not part of the algorithm. This is just a synthetic data generation tool. And then I split that data set into 80% training and 20% testing. Once again, a standard machine learning procedure. Now I move on to the hyperparameters of the classifier. So the hyperparameters of the classifier comprise basically, if we just talk about the classifier's own hyperparameter, it's just regularization, lambda. But then the classical part of the learning is about selecting the best possible ensemble. It could be an ensemble of trees, but even within those trees, you have got different hyperparameters of the trees. There is depth, there is uh, like splitting criteria, what kind of criteria could be used, and the stem length, etc. So we just keep all of the parameters default, and the depth value, we set it to 3. 3 is actually a good compromise between creating really complex learners or really, decision stumps. So yeah, we choose here the value of 3. Regularization value could be chosen, but this is something that can also be optimized using such procedures as randomized grid search, etc. And the class weight is one of the parameters of the ensemble as well. And this is once again a classical parameter. And I'm choosing the number of learners to be 10 because I'm limited by the exhaustive optimizer. So here I basically, first of all, I create the classical ensemble and I train it. And then I can use the ensemble.learners parameter to get the trained learners. And here basically internally, it initializes the ensemble. And when I would run the fit method, what it would do is that it would use the exhaustive optimizer to minimize the cost function that I was showing you before. So I just initialize my optimizer here as well, which takes the learned ensemble, the trained ensemble and the train set along with the regularization parameter. This is the core function, the main function that takes care of calculating the cost function for each of the different possible states and getting the state that's with the minimum cost that corresponds to the minimum cost. So inside the fit method that is done, and once it ends, I just have a trained quantum boosting classifier. I can use it to run a prediction on previously unseen test set. And if I do that, I basically get the training time to be 0.5 seconds, because this is a small ensemble and we are using the exhaustive optimizer. It really is fast. And the accuracy, recall, and precision. Actually, I can just run it really fast here. Uh, just a minute. Okay, yeah. So here in this case, and the optimization has resulted in five of the five of the learners to be discarded and five are kept. I can actually also print out that which of the learners have been kept by what are the weights basically. So you can see that four of the learners here, first four are kept, and then fifth one is dropped, sixth one is kept. So this way, we have finally basically five learners in the ensemble. Other five have been found to be either highly correlated with the other learners or highly correlated with the ground truth. So yeah, since this is a really small data set, a two-dimensional data set, we can actually visualize the decision boundary ourselves, how it looks, how the results look. There is this blue class here, then there's a yellow class here. As I was saying, that it creates a linear, no, a non-linear decision boundary between them. So it's it is not something that can be solved by a, let's say, a linear support vector machine as well. But yeah, okay. Yeah, so this was just a synthetic example. I would now like to show the same thing for the real world example. Um, the specific use case I would like to share with you is the grid stability use case. So the context is that ever since the adoption of renewable energy sources, it has provided us with much needed alternative to climate unfriendly fossil fuels. And it has allowed us the opportunity, allowed the consumers the opportunity to become prosumers. And it has also come with its own set of challenges. So first of all, the management of supply and demand becomes very challenging. And secondly, this kind of situation basically increases also the probability of grid instability, which, if not forecasted correctly, could lead to potential loss of resources, lives, etc. So this data set is really an open source data set that can be found on Kaggle and played with. It comprises of thousands of instances, each of which is described by 12 different features. And each of these instances is labeled as either stable or unstable. So each data point basically corresponds to whether the grid was stable at that point or unstable. So it can be easily formulated as a binary classification problem where you have grid stability and instability as the classes. And the goal would be, um, and the goal for us is here to train a quantum and classifier as we have got. to differentiate between the two classes. And it can be later on maybe used in production once it is made to reach that level. It can be used in production um, to predict such grid instability instances. So here's basically some data set that we have got from, as I was saying, it has 12 different features, and the labels are zeros and ones. And grid stability and instability. So this is a imbalanced data set. First step after the after splitting the training and test sets. In this case, we have already got the data set split, and we have got a separate CSV for training and test set. Since it is a highly imbalanced data set, the first step is to make sure that the training set is balanced. So what we do is that we use a random oversampler to oversample a bit the minority class to make it to equalize it with the majority class, which in this case is grid stability. Grid instability is more rare. So once we have balanced the two classes, everything else follows just as before. We create an ensemble, maximum depth of 3. It's made up of decision trees. We are using, once again, 10 learners. Regularization is a hyperparameter that can be optimized. What I've done is here is just for the ease here. First, I had a value that was similar to the previous one, the synthetic one, and I found that it basically was not penalizing any of the learners. So I increased it a bit. I actually increased it quite many-fold because I first increased it a bit and then I saw it still didn't lead to any penalization of the learners until I just got something like 7 out of 10. Now, this is also a bit of a rule of thumb that if you can get at the end like 60% of the learners in the ensemble, in the optimized ensemble, that is usually a good optimization. It usually results in good performance, but this is just something from experience. So there's a regularization term here that leads to us having 70% of the learners after the optimization. And I follow the same procedure as before, initialize the classifier, set up the optimizer, and do the fitting of the classifier. It takes about 2.47 seconds for this problem. And then I run the prediction basically, and there are metrics that are calculated: accuracy, recall, and precision. And for the sake of comparison, also I run the same thing with the same number of learners with the AdaBoost, and you can see the performance is very, very comparable. Precision turns out to be 100% in both cases, but accuracy and recall are more or less the same. As I said in the start, the goal of this notebook is not to present to you the best classifier for each of these problems, rather something that is understandable, and what is the how does the algorithm work and what's the simplest implementation. But these results could be improved significantly if we start on increasing the number of learners. For example, if we are using, let's say, D-Wave optimizer, or even simulated annealing optimizer, although that would also put a bit of a limit on how far can we go. But we can surely have much more than 10 learners in the ensemble. And then once again, we can bring in, since this is a really simple classifier, we can use grid search kind of procedures to do the hyperparameter of the regularization parameter. There's also an important feature of this classifier that if you just concentrate on regularization, it should be enough. You don't need to optimize the weak learners. Just weak learners could be decision trees, simple decision trees with all values set to default, and you can just focus on the regularization parameter. And basically that means that already reduces a lot of time that is spent on training. I compare this to, for example, random forest. If someone is using to solve a random forest to solve a similar kind of problem, and they usually end up running hyperparameter optimization over a large grid of many parameters, this is not required for quantum boosting. So yeah, basically, I don't have anything else to talk about related to this classification algorithm. I didn't run it. Maybe I'll just, for the sake of completion, I run it. If you guys have any questions, just feel free to ask. I'm basically done with my demo.